Hello. In today's lesson, we will discuss the concept of electric field. What does a field means? Now, look at this board one more time. I have an electrically charged plastic sheet. If I bring it near the electric ball, you can see what does it do? Well, this carries a negative charge. This also carries a negative charge. You notice that the ball is being pushed away. Now what that means is this charged object is now under the influence of this charged object. You see that? Well, I'm going to, all right. Now they are charged equally. There you are. Now, why is this force happen? The force happens because this ball is placed in the electric field of this charge. Now, that is the reason why the forces exist. Now, one more time. A charge exerts a force on another charge. Yes. You can see this charge exerts a force on the other charge because this charge is now placed in the electric field of this charge. So how will you define an electric field? Well, I can say, you see, I can place it anywhere here. That charge is being pushed away. So I'm going to define an electric field using this concept. How am I going to define it? Electric field of this charged object is a three-dimensional space around that charge where it will exert force on other charges. Isn't that a good definition of electric field? So what is the definition of electric field? Electric field is a three-dimensional space around a charge where it will exert force on other charges. Now the concept of a field is not only used to explain forces between electric charges. It can be used to explain forces between magnets, the forces between objects like gravitational force. All these forces can be explained by using the concept of a field. Force between two objects, whether it is electrical, gravitational, or magnetic, can be explained using the concept of a field. Now, a three-dimensional space where a force can be detected is a force field. Is that right? A force field is a region, a three-dimensional region where a force can be detected. For example, the space around the Earth where the gravitational pull of the Earth can be detected is the Earth's gravitational field. Now, if I drop this ball, why does the ball fall? It falls towards the Earth because it is placed in the Earth's gravitational field. Anything that is thrown up comes back because the objects are in the gravitational field of the Earth. The region around the Earth where it will exert force on other objects is called the gravitational field of the Earth. Here I have the Earth, and anything that is placed around it will be pulled towards the Earth because of the gravitational field. An object of mass m has a weight mg because of the gravitational pull. See, the moment you take the object away from the gravitational field, that object will lose all its weight. There will be no more force on it. In the same way, there is a space around an electric charge. Now, if this is the electric charge we are talking about, there is a space around that electric charge where it will exert force on other charges. And that space or that region is called the electric field of that particular charge. All right. This space is called the electric field of that charge. A positive charge attracts a negative charge because the negative charge is in the field of the positive charge. You see, this is a positive charge. It attracts a negative charge because this negative charge is placed in the field due to that positive charge. Alright, let's see, we can look at a visualization of the electric field. Now, if the yellow ball at the center is a positively charged object and a large number of tiny test negative charges are placed in the region surrounding that, look at the way all these charges are falling towards it. Now, doesn't it behave almost exactly like the gravitational field of the Earth? All these negative charges are placed in the field due to this positive charge. So here we have a good visualization of electric field. Electric field of this charge, the yellow object there, is a three-dimensional space around it where it will exert force on other charges. That means if all these are negative charges, those negative charges will be pulled towards it. What happens if you place similar positive test charges in this region? They will be all repelled away. So here is a good illustration of electric field. We will now discuss the concept of intensity of an electric field. What does that mean? Intensity. How intense is the electric field? In other words, intensity of an electric field gives us an impression on how strong the electric field. How do we calculate the amount of force that a particular charge experiences when placed in an electric field? Now, electric field is a vector quantity. Why is it a vector quantity? Because it is measured in terms of the force experienced by a test charge. It has a magnitude and a direction. The magnitude of the electric field is called the intensity of the electric field. In other words, the intensity of the field is the strength of the field. How strong is the field? Now we will represent the electric field by the letter E. And when you use a vector, we will represent this by an arrow at the top. So E with an arrow will be the electric field vector. The intensity of electric field E. So at the moment we are only considering the intensity, the magnitude of the electric field. Now how is it defined? It's defined as the force experienced per unit test charge placed at that point. So if I want to determine the intensity of the electric field due to this charge, now here is a charge here. If I want to find the intensity of the electric field at a point where my pointer is, what all I need to do is place a test charge there and measure the force it experiences. And the test charge, what is our test charge? You see, because we have two types of charges, a positive or negative, we must choose between them. And all over the physics community, it is understood and accepted that we will use a positive charge as a test charge. So if I place a unit positive charge here, the amount of force that unit positive charge will experience will give me a measure of the field intensity at that point. So one more time, electric field intensity is defined as the force experienced per unit test charge placed at that point. Electric field at a point is a vector quantity. It has both magnitude and direction. The magnitude of the field is what we call the intensity. And it becomes the field vector when you combine the intensity with the direction of the field. Now, let's consider a charge Q0, which is a test charge, placed at a point P, distance r from a charge Q. Now, this is the charge Q. Alright, our point P is here, and point P is at a distance r. This distance is r, and we place a test charge Q0 there. And of course, remember, a test charge is a positive charge. That means this test charge will experience a force due to this charge Q. What is that force? Can you tell me? If you know Coulomb's law, you can tell me that force. Using Coulomb's law, the force on Q0 due to this big charge Q is F equal to K Q Q0 over R squared. Now, this is a measure of the force on this charge Q0. And therefore, if I place a unit charge there, what will be the force per unit charge? The force on a charge Q0 is this. What will therefore be force per unit charge? The force experienced by a unit charge placed at P will be this force divided by Q0, because this force is experienced by a charge Q0. Therefore, what is the force per unit charge? It will be F over Q0. And when you divide this F by Q0, the Q0 will cancel, giving us KQ over R squared. This is a very important quantity. What does that represent? It represents the intensity of the electric field at a point distance r from a charge Q. Intensity of electric field at a point distance r from a charge Q is KQ over R squared. So E, what does E stand for? Intensity of electric field at a point distance r from a charge Q is E equal to KQ over R squared. Don't forget that. We need that right through the course. Alright, so what's the unit for measuring E? Remember, the E is measured as the force per unit charge. Force is measured in Newton, charge is measured in Coulomb. Therefore, electric field intensity, which is the force per unit charge, is measured in Newton per Coulomb, force per unit charge. If a charge Q coulombs is placed in an electric field E Newton per Coulomb, what will be the force on the charge? Tell me, what do you understand by an electric field E? E is the intensity of the field. This is the force per unit charge. Now, in this field, if you place a charge Q, what will be the force that charge will experience? It will be that field multiplied by Q. Why? Because by definition, field is the force per unit charge. Therefore, the force on a charge Q will be the force on unit charge multiplied by that charge. So by definition, E is the force on 1 coulomb of charge. Therefore, force on Q coulombs of charge placed in that field will be F, the force, equal to Q multiplied by E. That means whenever you place a charge in an electric field, that charge will experience a force. In the same way, whenever you place an object in a gravitational field, it experiences a force. This object is being pulled by the earth. it experiences a force, and that's why it falls. In the same way, a charge Q placed in an electric field E will experience a force given by F equal to Q times E. The charge Q will accelerate. Whenever there is a net force on an object, that net force will produce an acceleration. Now, what is the relation between force on an object and acceleration? F equal to ma, is that right? We will look at that as we go on, and we use this concept to solve problems. Now here I have a positive charge placed at a point. That means all around it there is an electric field. So what happens if I place an electron here? That electron will experience a force. How much force? The force on it will be its charge multiplied by the electric field. Now watch what happens when I place an electron there. There's an electron there. It is falling towards, just like my basketball falls towards the earth. If I place an electron there, it will fall towards that positive charge, because all around here there is a field produced by that positive charge. If I place the electron here, I can place the electron anywhere I want. I would like you to watch the little arrow on the electron. Now you can see as the electron nears the positive charge, the arrow grows. Is that right? The arrow becomes bigger. What does that mean? That means the electric field becomes greater. Where is the electric field greater? Is it near the positive charge or away from it? As you come closer and closer to the charge, the electric field becomes greater. There you are. Okay, we will use that concept also as we move on. We know that electric field is a vector quantity. It has a magnitude and a direction. Now, what is the magnitude of the electric field at a point distance r from a charge Q? The magnitude is E equal to kq over r squared. Now let's talk about the direction of an electric field. What is the direction of an electric field? Well, to determine the magnitude, we used a test charge. What is the test charge we used? A unit positive charge. We will use the same in determining the direction of the electric field. The direction of an electric field is the direction in which a positive test charge would move. So if you place a positive test charge, the direction in which that positive test charge would move is the direction of the electric field. Well, since a positive charge will move away from a positive charge, the field due to a positive charge is directed away from it. Is that right? If you have a positive charge and if you place a positive test charge near it, what will happen to that positive test charge? It will be repelled away. That means the electric field due to a positive charge will be directed away from it. In the same way, the electric field due to a negative charge will be directed towards it. Now, if I have a negative charge here, and if I place a test charge, a positive test charge, it will move towards the negative charge. So, the direction of the electric field is defined in such a way that the electric field is directed away from a positive charge and towards a negative charge. Let's illustrate that. Now, here I have illustrated that. Tell me, here you have electric field all directed towards in here. What kind of a charge is this? Well, this is a negative charge. The field due to a negative charge is all directed towards it. In other words, if I place a positive test charge anywhere here, it will move towards that negative charge. Whereas, look at the field due to a positive charge. If I place a unit test charge, a test charge is always positive. If I place a positive test charge anywhere here, it will be repelled away. That means the electric field due to a positive charge diverges from the positive charge. Let's now talk about electric field lines. Once you understand how the direction of the electric field is defined, we can now understand electric field lines. The intensity and direction of an electric field can be better understood by drawing what are called lines of forces, called field lines. What is a line of force? Again, you bring back our test charge. A test charge placed inside an electric field will experience a force, and due to that force it will move, and the path that it will follow is called a line of force. So what is a line of force? A line of force is the path taken by a positive test charge. Remember, our test charge is our guiding charge. So a line of force is the path taken by a positive test charge placed in the electric field. Since a positive charge always moves away from a positive charge and towards the negative charge, the field lines will always originate at a positive charge. Is that right? Lines will be starting at a positive, going away from it, and going towards a negative charge. Did you understand that? A line of force is the path taken by a unit positive test charge. That means if you place a unit positive test charge near a positive charge, it will move away and it will move towards the negative. That means the path taken by that test charge will be directed away from a positive charge and towards the negative. Alright? And so a field line will start at a positive and end in a negative charge. Now, let's now talk about some properties of field lines. We can summarize the properties of field lines. Property number one: field lines always originate at a positive charge and terminate at a negative charge. Is that right? It's not difficult to understand. Suppose I have a positive charge placed here and a negative charge placed there, and I have a test charge. A test charge is a unit positive charge. You can see that will move away from the positive and towards the negative. If you place it there, it will go that way. If you place it there, it will go that way. In other words, these are what I called the lines of force, the field lines. So a unit test charge placed near this positive charge will move away from it and move towards a positive charge. Field lines always originate at a positive and terminate at a negative charge. Second property: the density of the field lines, that is the number of lines per unit area, is proportional to the strength of the electric field. In other words, what it tells you is, if the field strength, if the field is very strong, the field lines will be very crowded there. Whereas if the field is very weak, the field lines will be widely separated. Let me show that here. Now, if I have a positive charge here, look at the field lines I can draw. I can draw a large number of field lines, and I have drawn two circles on it. You see, these are all paths that will be followed by a test charge. Now look around here. The field lines are rather close to each other. As you go away, the field lines are separated. Now tell me, where is the strength of the field maximum? Is it here or here? As you move away, the field becomes weaker. So the density of the field lines, in other words, how close the field lines are, is proportional to the strength of the field. Where the field lines are closer, the strength of the field is greater. That is what the second property says. Well, I have a diagram here. You can see where I have this halo-like ring. The field lines are very close to each other there. As you move away, the field lines get more and more separated. That means the field becomes weaker. Alright? The field lines are farther apart here than here. Therefore, the strength of the field is much greater here than here. Property number 3. The number of lines originating from a charge or terminating at a charge is proportional to the magnitude of the charge. In other words, the lines will be crowded around a large charge and less crowded around a small charge. Well, I'll illustrate that in a minute. Property number 4, field lines always repel each other and they never cross. You see, a field line is actually the path taken by a positive test charge. If two positive test charges move, can they ever cross each other? No, because positive charge always repel a positive charge. And that is the meaning of this property. Field lines can never cross each other. They always repel one another. The strength of the field in a region is uniform if the field lines are parallel. Now, parallel field lines indicate that the strength of the field all over is the same. But that is understandable from property number 3. So go through these properties and make sure that you understand the meaning of these. Well, here I have illustrated the meaning of density of electric field. If you look at charge A, there are only very few lines of force starting from there. Charge B has a lot more. Charge C has large number of lines of force or field lines starting from there. Tell me, using property number 4, which of these is contains the largest charge? A, B or C? Property number 4 is the number of field lines originating or terminating at a charge is proportional to the magnitude of the charge. You can see from A only very few lines originate, whereas from C large number of lines originate. That means C is a much bigger charge than A. And also look at the density of the field lines. The density of the field lines is much greater around C than around B and is much greater than around A. The density of the field lines indicate what? The strength of the electric field. So if you take a point here, the strength of the electric field here will be much greater than the strength of the electric field here, will be much greater than the strength of the electric field there. Alright? Okay. Let's now talk about yet another important concept. Electric flux. What is the meaning of a flux? Flux is really a something that flows, is that right? Flows across something. Flux. All right. The intensity of an electric field can be defined using the concept of lines of force that we have already done. The intensity of electric field E at a point in an electric field is defined as the number of lines of force crossing at right angles to a unit area containing that point. Suppose we have some lines of force coming from one end of the room and crossing this area. You see, if I want to find the electric field at this point, what I'm going to do is I keep an area of 1 square meter containing that point and measure the number of lines of force crossing that area. In other words, the number of lines of force crossing per unit area containing that point is a measure of the electric field at that point. You can see we are coming on to discussing the concept of flux. Now here you can see lines of force moving from left to right and crossing this area, right? Now what is the definition of electric field I gave you? If I want to define the electric field here, all I need to do is measure the number of lines of force crossing at right angles to a unit area placed there. In other words, number of lines of force crossing at right angles to a unit area containing that point is a measure of the electric field at that point. And here is another illustration of electric field lines crossing a given area. Alright? I hope you got a concept of what it means, electric field lines crossing a given area. Well, the number of lines of force crossing at right angles to any given area is called the flux crossing that area. The flux crossing that area. So, if I have a total area A here, the number of lines of force crossing that whole of that area is called the flux crossing that area. You see, what did we say the electric field is? Electric field is the number of lines of force crossing unit area containing that point. But flux is the total measure of the lines of force crossing the entire area. And so, we can use the concept of flux to define intensity of electric field. A flux is a measure of the total number of force crossing the entire area. If you divide that flux by this area, I will get the flux per unit area, and that will be a measure of the electric field. Alright, we will represent the electric flux by the Greek letter phi. Alright, so the electric field E is then the flux per unit area. In other words, E equal to phi over A. I want you to look at this carefully and learn it. We are going to use it in the next lesson. So you must be very well thorough with this. What is the definition of electric field using the concept of electric flux? E is flux per unit area. Flux is a measure of the total number of lines of force crossing at right angles to a given area. An electric field is flux per unit area. Number of lines of force crossing at right angles to a unit area. So electric field intensity is flux per unit area. Therefore, flux, the total flux will be electric field multiplied by the area, and that is measured in Newton meter squared per coulomb. Phi, electric flux crossing a given area will be E times A, where E is the flux per unit area. So flux per unit area multiplied by the area will be the total flux crossing that area. Alright, let's have a look at the concept of flux one more time. Here is an illustration of an electric flux. If you notice, there's a large number of lines of force going from left to right and crossing an area. This is a side view of, in other words, the area is kept like this. And now if you look at it from the front, this is what you see. Each of these dots is a line crossing. Now what happens if I tilt the side? You can see the flux is going to be less, because remember, flux is a measure of the lines of force crossing the area, the normal lines of force. In other words, we should consider the lines of force at right angles to the surface. Now, see what happens to the flux when I change the angle of the plane. Now, as the angle of plane is changed, you can see the flux is becoming now less. The number of lines of force crossing at right angles become less as the surface is now inclined to the lines of force. You can see as the angle, if I incline it more and more, the flux will become very small. And finally, what will be the flux to that surface when the surface is parallel to the lines of force? There will be no flux. That means I can increase the flux through a surface by making the surface more and more at right angles. And the maximum flux crosses the area when the area is at right angles to the surface. It's very important to understand that. We will now look at electric field due to a system of charges. In other words, if I have more than one charge placed in a region, electric field at any given point will be the vector sum of the field produced by each of these charges. Is that right? Electric field is a vector quantity. So what will the field look like if you have a system of charges? If a region contains more than one point charge, the field at any point is the vector sum of the field due to each of the charges in that system. Alright, consider two positive point charges as here. A is a positive charge, B also is a positive charge. That means if you take, say, this point where I'm pointing. Now, at this point, there will be a field due to A, I'm going to call it E sub A, and there will be a field produced by B, I call it E sub B. And each of these fields is represented by an arrow. Now tell me, why is the blue arrow E sub A smaller than the green arrow E sub B? Well, because B is closer to this point, that means the intensity of the field is greater at this point due to B than due to A. A is farther away. So the field at this point due to A will be small. And the strength of the field at this point due to B will be larger. And the net field at this point will be the sum of these two. Now, you know how to add vectors, is that right? You can actually draw a parallelogram with these as the two sides, and the diagonal will then give the resultant. That means the resultant field will be therefore this. The resultant field in here will be that. So every point there will be two electric fields, one due to A and one due to B, and the net electric field at any point is the vector sum of these two. All right. You can construct some of those in there. Now there are two field vectors at every point. The field at each point is the resultant, which is the vector sum of these two. For example, the field here, this is the resultant. I'm sure you understand why that is a resultant. Here, that is the resultant. And here, this is EB, this is EA, therefore that is the resultant. And here, EA and EB both are in the same direction. And look at the resultant field there, they can simply add up. Alright, let's now draw the net field due to two positive point charges. If you now draw, rather than drawing them individually, if you draw the net field, how will it look like? Look at this. The field due to two positive charges will look like this. A positive test charge placed here will move away. Well, it wants to move away from both charges. That means the field due to the two system will look like this. The field lines will be diverging from both. Why is this space in between? What is the specialty there? You can see the field due to the first charge is equal and opposite to the field due to the second charge. There will be no field in between. Right? How about the specialty here? The field lines are almost parallel. What does that mean? If the field lines are parallel, it tells you the field in that region is almost uniform. Field is not changing. So you must be familiar with these kind of drawing field lines. Now tell me, if this represents the electric field lines due to two positive charges, what will be the field due to two negative charges? Can you try and construct one on your own? Try before I go to the next slide. So there is a point between the two charges where the net field is 0. Okay, field lines due to two negative charges. Well, this time I'm going to have two negative charges. The only difference is the field lines, instead of converging onto the charge, in the case of positive charge, the field lines were diverging from each. In the case of negative charges, the field lines all will converge to the negative. So the only difference between this and the previous case is that the field lines are now converging to the negative. In the previous case, they were all diverging from the positive. Otherwise, the nature of the field is exactly the same. The resultant field due to two equal points negative charges is similar to the field due to two equal positive charges, except for the direction of the field. Alright? Field lines due to two opposite charges. If I have a negative charge and a positive charge, how will the electric field look like? Well, look at this. That is the positive, that is the negative. A test charge placed near the positive will move away from the positive and towards the negative. So the field lines originate at the positive and terminate at the negative. Isn't that beautiful? What a beautiful pattern of field lines. Now, you should also try and understand this. The strength of the field is much stronger where I am circling with my pointer and much weaker over here. And what can you say about the strength of the field in between the two charges? You can see the field lines are very nearly parallel there. So you have an almost uniform field in between the two charges. Why? The field lines originate on the positive and terminate on the negative. In the region between the two charges, the field lines due to both charges are in the same direction, because the positive will push the test charge away, the negative will attract. So look at the direction of the field lines in between there. The intensity of the field is high in this region. The field lines are very close there, and so the strength of the field will be very high in between the two charges. Okay. Look at, I have got some systems in here, and see whether you can understand these field representations. Look at this one. Here I have one positive charge and another positive charge. Can you tell me what is the difference between these two charges by looking at the field lines? Well, first of all, there are a lot more field lines originating from this positive than the one on the left. What does it tell you? It tells you that this is a much greater charge. You see, the number of lines of force originating or terminating on a charge is proportional to the quantity of charge. So this is a much bigger charge than this. Alright, we had a similar negative charge situation. Which of these carries a greater amount of charge? The one on the left or the one on the right? Obviously the one on the right, because large number of field lines are concentrating on it. Look at the third one. A positive charge and a negative charge. Tell me which of these charges carry a greater amount of charge? Well, the amount of charge is proportional to the number of field lines either originating or terminating. You can see the number of field lines terminating on the negative are much greater than the number of field lines originating at the positive. So obviously this negative charge represents a much larger quantity of charge. And how about this? Which of these has a greater amount of charge in it? Obviously the positive charge. Okay, now that you understand the basics of electric field lines, I'm going to give you an exercise, and this is the exercise. Several electric field lines patterns are shown in the diagrams below. Which of these patterns are correct? Explain what is wrong with each incorrect diagrams. Now, each one will earn you 1 extra credit point. Alright? I'm just going to show them to you, and I will leave them for you to answer and send them to me. You have this all on the PowerPoint, so I'm going to go a little fast. You look at the PowerPoint and then answer those and send them to me. Alright, here is the first set of diagrams. Diagram A, diagram B, C, D and E. You got to see which of these patterns are incorrect. Explain what is wrong with the incorrect diagram. Okay, that is number 1. Number 2, John drew the following electric field lines for a configuration of 2 charges. What did he do wrong? And explain. So this is the second assignment. Each one will give you 1 point. It's very silly actually, because it's so simple. Okay, you got to tell me what is wrong with the diagram and explain. Consider the electric field line shown in the diagram below. From the diagram, it is apparent that object A is dash and object B is dash. In other words, does it tell you anything about the type of charge carried by A and B? That is what I expect here. Alright, that is number 3. Number 4. Consider the electric field lines drawn at the right for a configuration of 2 charges. several locations are marked on the diagram. You need to rank these locations in the order of the field strength. In other words, which point the electric field is strongest, which is the weakest. Now you got to arrange those points in some ranking order. Now here are the points. Point A, B, C, D, E. You got to rank them according to the strength. Which of these 2 points has the field strength greater? Looking at the field pattern. Alright, that is number 4, I think. Alright, one more. I think there are 2 more. Use your understanding of electric field lines to identify the charges on the object in the following configuration. You got A, B, C, D, E, F, G, H, I. You need to identify the type of charge carried by each of these charged objects by looking at the field configuration. And finally, observe the electric field lines below for various configurations. Rank the objects according to which has the greatest magnitude of electric charge, beginning with the smallest charge. So you put the smallest first and then go in the order of increasing amount of charge. Alright, we got objects A, B, C, D, E, F, G, H, I, J. You got to say which has the greatest amount of charge in each of those. So there are 6 assignments that carry 6 extra credit points. So send them to me within a week and you can earn those points. And also go through and refresh these ideas. All the ideas that we discussed so far are going to be used in the next few lessons. Alright, so you must be very, very thorough with the concept of the definition of electric field, the definition of field lines, the definition of electric flux, the definition of electric field using flux. Is that right? Field strength. Electric field is flux per unit area. So all those concepts are very important. Alright, I'm going to stop this one here. I will see you for the next part of this lesson, which will be calculations using electric field concept. We will calculate electric field due to systems of charges using the formula we developed in this lesson. Alright, I'll see you for that in a little while.